In this video, I want to talk about Karnaugh Maps and how they can help us to visualize, reduce the number of equations or the number of terms in Boolean equations and generally simplify our equations. So if you remember from before, we can simplify or minimize Boolean equations by combining the terms. So usually the way it happened was by using axioms and theorems that we saw. For example, let's say if we had an equation like this, y equals AB bar plus BC bar plus BC plus A bar B bar, or something like this, a very random equation. So one thing that we can see here is that between these two we have B to be common. So one thing we can do is that we can factor out B, and then we have C plus C bar, right? So now we know that C plus C bar, or more specifically C or C bar, this is going to be 1, because either C is 0, C bar is 1, which makes C 0 or 1, 1, or the other way around. Another thing is that between these two, we can see that B bar is common. So between the two, what we can factor out is B bar. So between these two, we have B bar, and then we have A plus A bar. And again, similar to the one before, this is equal to 1. Now, after one level of simplification, what we have here is that we have B or B bar. And now what we see here is that we have B or B bar, which again, based on the previous simplifications, we know that this is equal to 1. So the final function is 1. So as you can see, this function, which initially had 4 terms, can be simplified to a single value of 1, right? Of course, this is a very straightforward case, but it is not always that simplified. Depending on the equation that we have, we may not be even it may not be even possible to simplify it to this extent. So let's say if we have y equals AB bar plus A bar B. So we cannot simplify this further. We can write it as a form of A XOR B, right? But this still contains 2 terms, right? Even though we used a simpler representation. Of course, if we have access to an XOR gate, this one can be implemented like this, right? A, B, and then Y. While for this one, we need to have 2 AND gates and 1 OR gate, and also we need to have 2 NOT gates as well. So if we have, let's say, A here, and then let's just say we have B here. So for creating the first term, we need to do it like this. For the second term, we need to do it like this, right? So even though these two are equivalent, I wouldn't consider it to be minimized, right? This has to do more in terms of the implementation, rather simplification of the equations. While for the first one, we went from a 4-term function to only one single value. So this, I can say, it's an extreme form of simplification. So now that we saw these couple of examples, let's just go more specifically and talk about Karnaugh Maps. As I said, Karnaugh Maps are a way to visually or graphically minimize equations. And the main building block or the main theorem that the Karnaugh Maps are using is this one. We have PA plus PA bar, so P is a Boolean variable, A is another Boolean variable. So when we look at this, we see that P is common between these two terms. So we can simply factor out P, and then we have A or A bar. Again, we know from one of the theorems that this one equals 1, which makes the output to be only variable P. So the main theorem that Karnaugh Maps use is this theorem. So now that we saw this, and given the fact that we said Karnaugh Maps are a way to visually minimize equations, let's just try to see how we can transform a truth table into a Karnaugh map. So I start very simple. So let's just take a look at one function which only has two variables. So if you remember, for two variables, when we wanted to create the truth table, we only had four possible combinations. We said A and B either are both 0, or only one of them is 0, or both of them are 1. Right? So these were the four possible combinations that we had for the truth table of a function with only two variables. We said that each one of these combinations has a min term associated with it too. So let's just quickly write down the min term associated with any of these functions, any of these lines. For the first one, both of them were 0, so the min term was A bar, B bar, or A bar and B bar. For the second one, we had A bar B. For the third one, we had A B bar, and finally for the last one, we had A B. So now, since we are only having four possible combinations, the Karnaugh map that we have only requires 4 cells. So let's just quickly create the Karnaugh map that we have. So I draw a table with 4 cells. I put a divider line like this. On top, I represent variable A, and in the bottom I represent variable B. So this means that these columns representing what values of variable A we can have, and this one, these rows represent what values variable B can have. So since this is a single variable, A can be either 0 or 1. The same is true for variable B as well. It is 0 or 1. So far it was very simple. So now for each one of these cells, we can write the associated min term inside. So for this cell, B is 0, and A is also 0. So the associated min term for this cell is going to be A bar, B bar. What about for this one? A is 1, B is 0. So this is the min term that we are looking for. This is A, B bar. What about this one? Here A is 0, B is 1. So what we have is A bar, B. And finally for the last one, we have A, B as the associated mean term, since both A and B are 1. So as you can see, going from the truth table to this 2x2 K-map is very straightforward, right? So one thing that you should notice here is that if you look for the relationship between each one of these cells and their neighbor, their immediate neighbor, one thing that you notice is that from one cell to the next one, only one variable changes. So let's just magnify it here. For example, for this one, these two cells, we have A bar, B bar, and then A, B bar. As you can see, only the value for A is changing. It goes from A bar to A, or vice versa too, right? If you look at this one, you can say A is changing from A itself to its complement, right? So let's just take a look at another one. What about this one? We have A bar, B bar, and then A bar, B. Again, here as you can see, between the two variables that we have, only one of them is changing. So we have one change here and one change here. But what about this one? Is it true for these ones which are on the diagonal? So A bar, B bar versus AB. Here we have two of the variables that are changing. So here we have two change. So now between these three cases, these three examples that I just gave, which one is similar to what we are looking for? In the theorem that we are looking for, we have PA plus PA bar equal P. So as you can see, only one variable is changing while the other one is fixed, right? Because we want to factor out the variable that is fixed so we can simplify the equation. So between these three, this one and this one satisfy the theorem, while the last one doesn't satisfy the theorem. So because of that, we are only looking for neighbor cells that you can say are immediate neighbors. By immediate neighbor, I mean when you go one step to the right or one step to the left or up or down, right? Nothing on the diagonal. There are cases that the cell in the diagonal would also help us simplify the equations, but not in this case. So now that we saw the relationship between the truth table and the basic Karnaugh map and how neighbors can fit the definition or the theorem that we want to use or not, let's just go over a very basic function. So instead of the mean terms here, let me just erase this. And I just put a function y, and I just randomly say, okay, it has a 1 here, a 1 here, 0, and 0, right? I created this function at random. You can try any other combination for values of y2. And let's just redraw this Karnaugh map, but this time we include the values for y in the Karnaugh map. So we have 0, 1 here, 0, 1 here. So whenever a and b are both 0, we have 1. Whenever a is 0, b is 1, we have 1. And for the other two, we have 0. So when you look at this function, you immediately notice that, okay, these two ones are neighbors, and going from one to the other, right, only one variable changes. So if I want to write this function in terms of sum of product, we had to come up with the mean term associated with each row, and then or all those mean terms. So the mean term associated with this one was a bar, b bar. For this one, we have a bar, b. So we have a bar, b bar plus a bar, b. So from the theorem, we can easily see that a bar is common between the two. So we can factor out a bar, and then we have b bar plus b. This is simplified to 1, and then we have a bar here. So now that we saw this being simplified using the theorem, let's just see what happens if we want to use the Karnaugh map. So for the Karnaugh map, as you can see, these two ones are neighbors, immediate neighbors, and between the two, variable a is fixed as value 0, but variable b is changing from 0 to 1. So the way Karnaugh map works is that you look for the neighbor ones that have some fixed variables and some changing variables. So the variables that are changing, more specifically, if you have all the possible combinations of a single variable, that means that you don't have to include it in the final Boolean equation. Only the variables that have fixed values. For example, here a's value is fixed at 0, but b has all of its combination. It's either 0 or 1. So since a is fixed, we have it in the final function. Since it's 0, we use it as its complement, but b has both 0 and 1. So that means that we don't have to include it in the function. So this is how we can go from the truth table to Karnaugh map to the final Boolean equation without doing the intermediate steps, right? Of course, for this 2x2 Karnaugh map, the benefits are not that great, right? Because you can easily just write these two sentences and come up with your final function, right? But when you have 3 or 4 variables, using Karnaugh maps is much more elegant and straightforward than trying to use the theorems, right? Because for the theorems, let's just say if you have a 4 input function, so that means that you have 16 possible mean terms, right? So if your function has, let's say, 9 of those, applying the theorems one by one can be very time consuming and more specifically prone to error, right? But if you can do it visually, it's going to be much more simpler. So now that we saw this, let's just see how it looks like for the 3 input function. So if you remember again from before, when we have 3 input functions, we have 8 possible combinations. We have A, B, C as the inputs, and the values can change from 0, 0, 0 all the way to 1, 1, 1. Again, if you look, this is equivalent to 0 in base 10, this one is equivalent to 1 in base 10, all the way to 7 in base 10. Again, it is very beneficial if you have them all in order. So I emphasize again, learn how to count from 0 to 15 in binary. That makes your life much, much easier. So we have A, B, and C as the inputs, and here we have some random function. We call it 1, y, and for this random function we have y to be 1 for these two rows only, and it is 0 otherwise. So before we go to coming up with the function, with the Boolean equation for function y, let's just see how the 3-input Karnaugh map is being built. For the 2-input, it was very straightforward. You had two variables, you created 2 by 2 table, you put a divider line, and then on one side of the line you put your first variable, and on the other side you put the second variable. And the combinations were very simple too. So variable A could either be 0 or 1, variable B could also be either 0 or 1. When you have 3 inputs, it is a bit more complicated. So we create a 2 by 4 table because now we have 8 possible combinations. We put our divider line again. Now what we do is that we group the inputs. So for the columns, we use variable A and B, basically the combination of the two. For the rows, we only use variable C. And it can work if you, for example, use A only for the top and B and C for the rows, right? But this is what I'm gonna be using. The final result won't be different. So for variable C, it is very simple. It's either 0 or 1, right? There is only 2 combinations. But for AB, we have now 4 possible combinations. They either can be 0, 0, they can be 0, 1, they can be 1, 0, and then finally they can be 1, 1. So let's just quickly write these possible combinations. So if we have AB, we have 0, 0, 0, 1, 1, 0, and then 1, 1. So between the first row, the first combination, and the second one, how many changes do we have? We have 0, 0 changing to 0, 1. So as you can see, when we go from the first combination to the second one, only the value for B is changing. So we have 1 change here. What about going from the second combination to the third one? How many changes do we have here? As you can see, we go from 0, 1 to 1, 0. So here, 1 changes from, B changes from 1 to 0, and also A changes from 0 to 1. So here, we have 2 changes. And finally, for the last one, going from the third combination to the fourth one, we have only 1 change. So here we have only B changing from 0 to 1. So now let's just tweak these combinations. Let's just quickly change the order a little bit. So we have AB, what if I have 0, 0 again first, 0, 1. For the third one, what if I use 1, 1? And finally for the last one, what if I use 1, 0? So let's just see what are the changes that we have here now. From the first one to the second one, we have only one change in value of the variables. From the second one to the third one, we have again one change. Value for A is changing from 0 to 1. And finally for the last one, again we have one change. We go from 1, 1 to 1, 0. 1 is fixed, B changes from 1 to 0. So as you can see, what we can do is that by using a slightly different order, we can make sure that when we go from one combination to the next one, only one variable is changing. Why do we do that? If you remember, we want to use this theorem to do the simplification. So if the Karnaugh map is formatted in such a way that if you go from one neighbor to the next one, only one variable changes, you can easily use this theorem to do the simplifications. So this is what is usually called as regular counting. So this is the way that you regularly count, going from 0 to 0, 1, 2, 3, right? This is what is called the gray code. Basically, you just simply change the order of these numbers in such a way that going from one to the next one, you only have one change in the variables. So this is how we order the combinations of the columns of the Karnaugh map to basically have only one change from one cell to the next one. I can show the same result using the regular way that we count as well, so you can easily see the difference. So if we have, let's say, a Karnaugh map for 3 variables, and let's just say I use the regular way that we count. So if I quickly write down the associated min term for each one of these. So let's just say we have A bar, B bar, C bar. So as you can see, A, B, and C are all 0 here. For this one, we have A bar, B bar, C. For this one, we have A bar, B, C bar, and then A bar, B, C. For this one, we have A, B bar, C bar, and then A, B bar, C. And finally, for the last one, we have A, B, C bar, and then A, B, and C. So as you can see, from this one to this one, we only have one change. But from this to this, we have two changes. So we go from A bar to A, and we go from B to B bar, right? So this is two changes. So if we write down our Karnaugh map in this, we cannot group these two to basically simplify it, because they have two changes happening when you go from one cell to another. So this is a wrong Karnaugh map. So this is something that you should always keep in mind, and that is a very simple fact. But because it is simple, it is very common that you can overlook it, and then whatever function that you come up with at the end is going to be wrong. So now that we saw this, let's just see how we can simplify this function using Karnaugh Maps. Okay, so for this function, we have y to be 1 only for these two rows. So when a, b, and c are all 0, so this one, or when a is 0, b is 0, and c is 1, this one. So if we write down the associated mean term for all the cells of the Karnaugh map, what we can do is that we can just simply use the SOP approach, sum of product approach, to come up with the function for Boolean equation for this function. So if we do that, function y is going to be a bar, b bar, c bar plus a bar, b bar, c. So now between these two terms, we see that a bar, b bar is common, so we factor that out. So what we end up with is a bar, b bar multiplied by c bar plus c, or a bar, b bar ANDed by c bar or c. So now that we have done it, we know that c bar or c simplifies to 1. So if we do this, the final value or the final Boolean equation for y is going to be a bar, b bar. And again, as you can see, we just use the sum of product and the theorems to do the simplification. What if we want to do it using the Karnaugh map? So doing it using the Karnaugh map, basically you group the ones that are neighbors, immediate neighbors. You look at the variables that are common between the two. So between these two ones, you have a and b to be common as their complement. So a is always 0 between the two, and b is always 0 between the two. So you use a bar and b bar. What about c? Since you have all the possible combinations of c to be covered in the Karnaugh map, then you don't have to consider it in the final Boolean equation. So that means that your final Boolean equation is going to be a bar, b bar. And as you can see, it is similar to what we derived using the sum of product form too, and by applying the theorems. So what we do for using the Karnaugh map to simplify or minimize the Boolean equation, we first circle the ones that are in adjacent squares, and then for representing the function in Boolean expression, we only include literals whose true and complement forms are not in the circle. So this is a more sophisticated way of what I said before. So for example, for this function, I said that a and b are common between these two ones, and their value is always 0, while c has both of its values. So it can be 0 or it can be 1, right? So because of that, it is not going to be included in the final Boolean equation, while a and b are in the final equation. Why? Because their value is fixed. between these two ones that we have here. So now let's take a look at another example. So here we again have a 3-input function with values A, B, C as the input. Again, we ordered it so all the possible combinations change from 0 to 7 in base 10, or change from 0, 0, 0 to 1, 1, 1. We created the Karnaugh map. We created a 2x4 table. We used the divider line. For the columns, we are going to be using the columns to represent combinations of values, variables A and B, and for the rows we use them to show combinations or possible values of variable C. Again, we use the gray code, so we make sure that from each cell to its immediate neighbor, only one variable is changing. So now that we have this, let's just fill out this Karnaugh map using the values for the function y that we have. So when A, B, C, and R are all zeros, value for y is 0. For 0, 0, 1, the value for y is 0. For 0, 1, 0, which is this one, the value for y is 1. For 0, 1, 1, the value for y is 1. For 1, 0, 0, the value for y is 0. So this is the 1, 0, 0. For 1, 0, 1, the value for y is 0. Sorry, this one is 0. For value for 1, 0, 1, the value for y is 0. Then for 1, 1, 0, the value for y is 0. So 1, 1, 0. And finally for 1, 1, 1, the value for y is 1. So as you can see in this truth table, only 3 mean terms are present. So if I want to use the sum of product form, I can write y to be equal a bar b c bar plus a bar, this is for this term, b c, and finally last one, which is a b c. So this is the function in sum of product form. What if I want to use the theorems to simplify this? All I can see is that between these two, a bar b is common, so I can factor out a bar b, and then we have c bar plus c. And then if I do the simplification, so this is 1, I end up with a bar b plus a b c. So this is the function that I get if I use the theorems only to do the simplification. So now let's just see what function I get if I use Karnaugh map. So what we wanted to do was to circle the neighboring ones and then write a term for each one of the circles. So one thing I can do is that these two are immediate neighbors. So what I will do is that I circle these two together. What about this one? Does it have an immediate neighbor? Yes, it does. But this one is already being included with a circle with this one here, right? So does that mean that I cannot include this one with this one in a circle? The answer to that is you can, right? There is nothing that prevents you, so you can create another circle like this. So now based on this, let's just write down the function. For the first circle that I draw, let's just see what are common and what are changing. So between this one and this one, what is common? So the value for C is common. Why? Because when you go from this cell to this cell, the value for C is always fixed. So it is always 1. So that means that it is included in the term associated with this one. What about the value for A? The value for A is changing. So you have A to be 0 for this one, and also you have A to be 1. So since you have both the variable itself and its complement, that means that this variable is not going to be included in the Boolean equation, or more specifically in the term associated with this circle. What about B? B is included. Why? Because B has a fixed value. So it is 1 for both of these ones here. So that means that the term associated with this circle is going to be BC. So let's just do the same for the second circle that we have, this one. What is common between these two ones? We have A to be 0 for both of them, and we have B to be 1 for both of them. What about C? C can have both 0 and 1 as its value. So since it can have both 0 and 1, that means that it is not included. While we have A to be 0, that means that we have A bar, and we have B to be 1, that means we have B itself. So this is the final simplified equation that we can come up with using the 3-input Karnaugh map. So if you look closely at these two forms, 1 and 2. So 1 and 2 are equivalent, right? So don't make the mistake. They are exactly the same. If you do the implementation and you go through all the possible combinations of inputs A, B, and C, the value for Y is going to be exactly the same for both of these functions. But when it comes to implementation, this is simpler, right? Because it only requires two input AND gates and one 2-input OR gate. While for this one it requires one 2-input AND, one 3-input AND, and then one 2-input OR. If you don't have access to 2-input AND, that means that to implement this 3-input AND, you have to use two 2-input ANDs, right? So overall, the second one is simpler, right? You might ask, okay, we used theorems to simplify this first form, right? Why didn't we get the simpler representation, right? Why we ended up with this form that is still more complex than the second form? The answer to that is that when you are using theorems, right, you usually don't consider adding new terms that don't affect the outcome that much, right? What do I mean by that? Let's just take a look at the Karnaugh map, and let's just take a look at this one, right? As you can see here, this one is being considered in both of these circles, right? While in the in the sum of product form, you didn't, you only worked with 3 terms, right? So you can get the exact same result if you consider the possibility of adding some terms into your sum of product form. So let's just say you have a function x and it is AB plus CD, right? So is the function, let's just call this x1, and then let's just have a function x2, and now I have AB plus CD plus AB. What is the relationship between the function x1 and x2? Are they different or are they the same? For the first one, you have only 2 terms, A, B, C, D. For the second one, you have A, B, and C, D, but you have an extra A, B term too, right? If you remember from the theorems, we said that A plus A equals A, right? So that means that adding this additional AB term does not change the value for x2. So for all intentions and purposes, x1 and x2 are exactly the same functions, right? So now let's try to apply it to the sum of product form that we have here. So I rewrite this again. We have A bar B C bar plus A bar B C plus A, B, and C. So what happens if I add 1A bar B C? So as you can see, this one, this term, and this term are equal, right? So based on the fact that A or A equals A, or x1 and x2 are exactly the same here, so adding this term does not change the value for function, right? So now that we have this, you can easily see that between the first term and the second term, you can factor out A bar B, and between the third term and the fourth term, now you can factor out BC. So if you do the simplification now, you can see that this function is simplified to A bar B plus BC. So exactly the same function that we have here. So let's just call this form 3. So form 3 is exactly the same as form 1 and form 2. So when you are using Karnaugh maps, you basically conceptually including or adding some additional terms that does not change the value for the function, but it results in a simplified form for the function. So now that we saw this, before I give you the full set of rules for using the Karnaugh maps, let's just quickly go over the definitions that we had before. So we had the definition for the complement, which was a variable with a bar over it. So A bar, B bar, C bar. We had the definition for literals, which was a variable or its complement. We have the definition for implicant, which is a product of literals. So implicants basically contain all the min terms, right? But you can have implicants that are not necessarily all the possible min terms, right? So every implicant, every min term is an implicant, but not every implicant is a min term, right? And the reason for that is min terms require to have all the variables for their complement, right? While the implicant can only contain a few of the variables and not all of them. And finally, we have the prime implicant, which is the implicant that corresponds to the largest circle in a K-map. You will see what that means in a later slide. So now, based on this, we have the general rules for Karnaugh maps. So the first rule is that every one that you have for your function must be circled at least once. So that is the first rule that you should have. The second rule says that each circle must span a power of 2. So that means that when you're grouping the ones in your Karnaugh map, the number of cells in each group should be a power of 2. So it can be either 1, 2, 4, 8, 16, 32, right? And should be a power of 2 in each direction. So that means that you cannot have 3 cells in a circle. You cannot have 5 cells in a circle. It must be a power of 2, both in total and also in each direction. You will see when we are working with 4-input Karnaugh maps how that works. Then each circle must be as large as possible. The next rule says that a circle may wrap around the edges, and that is an important rule. And finally, if you have don't care cases in your function, you have the option to include them in your circles or not, and it depends whether they minimize the equation or not, right? So these are the general rules that you can have for Karnaugh maps. So based on this, let's just take a look at a 4-input Karnaugh map. So for 4 inputs, if we create the truth table, we have 16 possible combinations. So this is equivalent to 0 in base 10, and the last one is equivalent to 15 in base 10. Again, to make everything simplified and organized, we put them all in regular order, right? So again, try to learn how to count from 0 to 15 in binary, or go from 0, 0, 0, 0 to 1, 1, 1, 1 in binary. Now, based on this truth table, we want to create the 4-input Karnaugh map. We create a 4x4 table. We use the divider line. Here, for representation of the columns, we use variables a and b, and for representation of the rows, we use variables c and d. Again, as before, we use the gray code for the representation, and the reason for that is we want to have only one change from when we go from one cell to its immediate neighbor, right? So this is something that you should always keep in mind. If you don't consider that, all the calculations that you do later will be wrong. So now that we have this, let's just fill out this Karnaugh map using the values for y. So for the first one, we have 0, 0, 0, 0 for A, B, C, D, and the value is 1. So I put 1 here. Then we have 0, 0, 0, 1, and the value is 0. Then we have 0, 0, 1, 0, the value is 1. So 0, 0, 1, 0, the value is 1. And then we have 0, 0, 1, 1, the value is 1. So let me just quickly write it. So this is the first, this is the second, this is the third, this is the fourth row. So this is the first, this is the second, this is the third, this is the fourth row. So let's go to the next four. We have 0, 1, 0, 0, which is 0. 0, 1, 0, 1, which is 1. 0, 1, 1, 0, which is 1. And then 0, 1, 1, 1, which is again 1. So we got to this point. Next is 1, 0, 0, 0, which is 1. 1, 0, 0, 0, which is 1. 1, 0, 0, 1, which is 1. 1, 0, 1, 0, which is 1. And finally 1, 0, 1, 1, which is 0. So if I want to quickly write this, let's say this is 5, this is 6, this is 7, and this is 8. So this is 5, 6, 7, and 8. And finally, for the last four, we have 1, 1, 0, 0, which is 0. 1, 1, 0, 1, which is 0. 1, 1, 1, 0, which is 0. And finally 1, 1, 1, 1, which is 0. So now we have converted our truth table into the Karnaugh map. So now that we have this, we can use the rules for the Karnaugh map to do the simplifications. So let's just quickly look at the rules again. So the first one says every one must be circled at least once. Okay. Each circle must span a power of 2 squares in each direction. Each circle must be as large as possible. A circle may wrap around the edges. And finally, if we have don't care, we circle them only if they help us to minimize the equation. So based on this, let's just create a circle as large as possible that contains all ones. So what is that circle? So if I create a circle like this or a group like this, this is the largest circle that I can draw in this Karnaugh map that includes only ones. It cannot include zeros. And it spans as a power of 2 in each direction. So in the, let's say, horizontal direction, it has 2 cells. In the vertical direction, it has 2 cells, right? Do you remember when I said you cannot include diagonal cells? So if you look closely, basically we are not including diagonal cells. We just say these two are immediate neighbors, these two are immediate neighbors, these two are immediate neighbors, and these ones are also immediate neighbors, right? So the way it works is that because we have all these 4 to be immediate neighbors, that makes these 2 diagonal cells to be included in one circle. If let's say, for example, if this one was 0, if this one was 0, then we only had these 2 to be immediate neighbors, and this one was not included in this circle. But now, because all of these 4 are ones, so that makes them all to be neighbors, and because of that they can be included in a large circle. Okay, so this is the largest circle that I can draw at the beginning. What about all these ones at the corners? Are they part of a circle or not? So to answer to this question, it is beneficial to look at the mean terms that represent these four cells. So let me just quickly write down the mean terms that are associated with the four cells at the corners. So this one, the mean term associated with it is A bar, B bar, C bar, and D bar. For the second one here, we have A, B bar, C bar, and D bar. For this, we have A bar, B bar, C, D bar. Sorry, this one is A bar, B bar, C bar, D bar. And then for this corner, we have A, B bar, and then C, D bar. So now let's see how many changes do we have if we go from one corner to another. So if we go from this one, the top left corner, to the top right corner, what you see, we only have change in variable A. So we only have one change. So practically you can say they are neighbors. What about if we go from the corner at top right to the corner at bottom right? As you can see, A is the same, B bar is the same, D bar is the same, but C goes from C bar to C. So again, we have one change here. What about these two corners, bottom right and bottom left? We have B bar the same, C the same, and D bar the same. So that means that only one change is happening when you go from this corner to this one. And finally, when you go from the bottom left corner to top left corner, again, you only have one change. Only the value for C is changing, while A, B, and D are the same. So we have A bar in both of them, B bar in both of them, and D bar in both of them, but the value for C changes from C bar to C. So based on this, now the rule that we had in the previous slide that was saying that the edges can wrap around in Karnaugh Maps makes more sense. So you can think of a 4-input Karnaugh map as a torus, right? So do you remember what a torus is? It looks like a donut. So at any point in a donut, you can go up or down, right? And when you go through around the circle, for example here, if you go up and then you go around the circle, you end up at the same place. The same is true if you go in the other direction. If you go around the circle, you end up at the same place, right? So a 4-input Karnaugh map is practically a donut, a torus. If you go from here to the right, you come back from here, from the left. Or if you go from here to the bottom, the down direction, you go back up from the top direction, right? So that's what we mean by these edges wrap around. So now based on this, basically we can create another circle of size 4 by including all the ones in the corner. So we have this, this one, and this one. And again, this circle is only valid because it spans a power of 2 in both directions, right? Or in another word, the size is a power of 2. So the size of this circle includes 4 cells, which is a power of 2. If it was 3 cells, that didn't count, right? That couldn't be considered as one large circle. It should have been divided into 2 circles of size 2, similar to what we saw here before. So now, as you can see, most of the ones are included in circles. There are 2 left. So what you can do is that you can just simply create circles of size 1, and that is a valid case, right? But you see that you have some immediate neighbors that can be used again to create circles of size larger than 1. So we definitely do that. So based on this, we include these 2 circles of size 2 as well. So now all the ones that we have in the Karnaugh map are included at least in one circle. So since there are no ones left, we can write the simplified Boolean equation. So if I write function y, so let's just call this circle 1. Let's just call all the corners to be circle 2. Let's just call this circle 3. And I call this circle 4. So let's just write the associated implicant for each one of these terms. What we do is that we look for the variables or the literals that are common, and we include those, but for the variables or literals that have both their variable and their complement, we don't have to include that. So let's just go over what happens for circle 1. So between all these 4, the value for A is fixed, right? A is 0 for all of these 4. So that means that we have A in its complement form included in the implicant associated with this circle. But what about B? B has both 0 and 1. So that means that it is not going to be included. What about C? C is both 1 for all these 4 ones, right? Basically C is 1 for both of these rows, which basically include all these ones that we have in the circle. So that means that C is also included in the implicant associated with this circle. But what about D? D is both 1 and 0. So that means that we don't have to include it. So this will be the term associated with this 2 by 2 circle. Now let's just go for the second circle, the circle that encompasses all these ones at the corners. So for all these ones, as you can see, the value for A changes. It can have both 0 and 1. So since it has both the variable A and its complement, it is not going to be included. So A is not included. What about B? B is always 0 for all these 4 ones. So that means that we have B bar here. What about C? C can be both 0 and 1 for all these 4 ones. so that means that it is not included. On the other hand, D is always 0, which basically means that we need to have D bar in the implicant associated with this circle as well. So now let's just take a look at circle number 3. So circle number 3 has only 2 ones inside of it. So for these 2 ones, A is always 1, which means that we have A here. B is always 0, which means that we have B bar here. C is also always 0 for these two, which means we have C bar here, but D has both 0 and 1 values. So that means that it's not going to be included. Basically, if you write down the associated mean term for these 2 ones and then you use the theorems, you can simplify or minimize the variable D. And finally, for the last circle, which contains these 2 cells, we have A to be always 0, so we have A bar. B is always 1, we have B. C can be both 0 and 1, so it is not included. And D is always 1, so we have D. So this is the simplified equation that we have for this function. So how many terms do we have? We have only 4 terms. 1, 2, 3, 4. What if we wanted to use the sum of product form to implement this function? How many terms did we need? 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So if we wanted to use the simple sum of product form, we needed 9 terms to represent this function. And each one of these 9 terms was a 4 input AND. But here we have 2 input ANDs and 2 3 input ANDs, plus a 4 input OR. But in the sum of product form for implementation, we needed 9 3 input ANDs and 1 9 input OR. Which, as you can see, using the Karnaugh map, we were able to simplify this function greatly. So these are the same calculations, but in a much nicer way. So now that we saw this, let's just take a look at one example with don't cares. If you remember from before, don't cares were the cases in which the value of the output did not matter for us, right? So let's just see how we can use these don't care cases to simplify our functions even further. So again, we have this sample function. It has 4 inputs, A, B, C, D, and the output is Y. And then we want to fill out this Karnaugh map using the values for Y. So for 0, 0, 0, 0, the value is 1. For 0, 0, 0, 1, the value is 0. For 0, 0, 1, 0, the value is 1. And for 0, 0, 1, 1, the value is 1. Then for 0, 1, 0, 0, the value is 0. For 0, 1, 0, 1, the value is X or don't care. For 0, 1, 1, 0, the value is 1. And for 0, 1, 1, 1, the value is 1. So this one is the last one that I just put it inside the table. For 1, 0, 0, 0, the value is 1. For 1, 0, 0, 1, the value is 1. And for the rest, of the values in the table, the value is going to be don't care. So don't care, don't care, don't care, don't care, don't care, and don't care. So as you can see here in this Karnaugh map, we have 1, 2, 3, 4, 5, 6, 7 cells to be don't cares. So are these going to be beneficial when we want to do the simplification of the Karnaugh map? The answer to that is most likely yes, right? So now let's just create these circles for this specific example, and we consider these don't care values as 1 whenever they help us simplify our function. Basically, whenever they help us create larger circles. So just by looking at this, I can easily see that if I create this very large 8-cell circle, right, that is basically the largest circle that I can have. I can do the same here too. I can create another 8-cell circle. So as you can see, I consider these don't care values to be 1, right? Since they are don't care, we basically don't care about their values. So if assuming that the values are 1 can help us simplify the function, I will do that. So this one only left, right? So as you can see, this one, he's on the corner. There are 2 other corners values that are 1, 2, but there is this last one that is considered to be don't care, right? So since we already included that in these circles, that means that we consider this one to be also 1, 2, right? So keep in mind, if you consider a cell to be a value of 1, you cannot change that, right? So it cannot be 1 for one circle and 0 for another circle, right? If you consider it to be 1 and you include it in a circle, that means that it is going to be a 1 for all of them too. So that means that now we can create this fourth circle of 4 corners, and then use this to basically come up with a more simplified form of the function. So now if I want to write down y, what I have is that I can start from the first circle, then this one was the second circle, and this one was the third one. So keep in mind that I always start with the largest circle, right? And then work my way down into the smaller ones, right? So for the first one, let's just see what we have here. For all these 8 cells, what is the value of A? A is both 0 and 1. So that means that A is not going to be included. What about the value for B? Again, for all these 8 ones, B can be both 0 and 1. So that means that B is also not included. What about C? C is always 1. So that means that we have C here. What about D? D has both 1 and 0 values. So again, D is not going to be included. So only one literal is representing all these 8 cells in the truth table. For the second one, we do the same. For all these 8 cells, value for A is always 1. So we have A. Value for B has both 1 and 0. So we don't have B. Value for C is both 0 and 1. So we don't have C. And value for D has both 0 and 1. So we don't have D either. And now for the third one. The third circle is all the ones at the corner. So as you can see, for all these ones, the value for A is both 0 and 1, so it is not included. The value for B is always 0, so we have B bar. The value for C is both 0 and 1, so that means C is not included. And the value for D is always 0, so we have D bar. So the final function is C or A or B bar, D bar. So as you can see, this function by itself had 1, 2, 3, 4, 5, 6, 7 terms, right? So if you wanted to use the sum of product form without the don't cares, you needed 7 min terms. But because we have these don't cares, we basically can simplify our function. And that is why we say for don't cares, we either consider them or we don't. How do we decide if we want to consider them? Do they simplify our function or not? For example, this one, it does not simplify our function. You can say I can create this, let's say, 2 by 2 circle right here. And you can do that, right? But if you created this larger 8 cell circle, right? So that means that there is no need to include this at all. So again, don't cares are only being considered if they help us simplify our function, right? If they don't help us simplify the function, there is no need to use them. So now that we saw this, let's just quickly go over a 7-segment display. So I'm sure you have seen this many times before. So a 7-segment display is basically 7 LEDs. So we have A, B, C, D, E, F, G. So this is the naming convention for 7-segment displays. What happens is that whenever you want to show a value on a 7-segment display, depending on the value, either some of the LEDs are on or off. For example, if you want to show value 0, then A, B, C, D, E, F are on while G is off. If you want to, for example, show value 4, B, C, F, G are on while A, D, and E are off, right? So because this is the case, we can come up with the Boolean expressions for the 7-segment display. For each one of these LEDs, we can come up with a truth table and write down a Boolean expression. So let's just do that for SA as a practice, and you can do for the rest of them on your own. So here what we have is we have a data input, basically the number that we want to display. So the data here, I showed it as the 0 the 3:0, which is equivalent to writing it like D3, D2, D1, and D0, right? Or if you prefer, you can write it as A, B, C, and D, right? So these are all equivalent. So the reason that it's been shown in this form is that if you are working with data, usually is that you use a single variable for a single name for your variable. So we assume that here the variable that we want to show has 4 bits. So that's why this is a shorthand version of representing this variable. So we call it D as in data. Since it's 4 variables, we know that the the bits can change from 3 to 0 or 0 to 3, right? And I show it in this format. You can just simply use A, B, C, D. In this representation, A, B, C, D, each one represent only 1 bit. So now based on this, we can create a truth table for all the possible combinations of the 7-segment display. So this is equivalent to 0 in base 10. This one is equivalent to 9 in base 10. And since this is only using to show 1 digit, so in 1 digit you can show values between 0 and 9, right? So that's why in this truth table I only show from 0 and 9. And for the rest, I consider the 7-segment display to be completely off. So now, based on this, we can create the truth table for all the LEDs. For example, SA is the function that shows the value for LED A. So when the value that you want to display is 0, that means that this is going to be on. So as you can see here, this is SA and it is on. For 1, it's going to be off. For 2, it is on. For 3, it is on. For 4, it is off. For 5 and 6, it is on. For 7, it's on. For 8, it's on. And for 9, it's on. And since for any value larger than 9 we want to have the 7-segment display to be completely off, then we set it to 0. And then you basically do the same for all the other columns that associate for the different LED. So now based on this, let's just come up with the Boolean equation for function SA. So since we have 4 inputs, I create a 4x4 Karnaugh map. I draw the divider, so here we have D3 and D2 representing the columns, and we have D1 and D0 representing the rows. We have 0, 0, 0, 1, 1, 1, 1, 0. Again, we are using the gray code. So from one cell to its immediate neighbor, we only have 1 change. And now that we have this, we can simply fill out this Karnaugh map using the truth table that we have. So for 0, 0, 0, 0, it is 1. For 0, 0, 0, 1, it is 0. For 0, 0, 1, 0, it is 1. For 0, 0, 1, 1, it is 1. For 0, 1, 0, 0, it is 0. For 0, 1, 0, 1, it is 1. For 0, 1, 1, 0, it is 1. And for 0, 1, 1, 1, it is 1. For 1, 0, 0, 0, it is 1. For 1, 0, 0, 1, it is 1. And finally, for the rest are going to be 0 based on what we have here. So this is for 1, 0, 1, 0, 0 all the way to 1, 1, 1, 1. So now we have this Karnaugh map. What we should do next is to come up with the circles, and we start from the largest to the smallest one. So the largest circle of size of power 2 that I can draw here is this one. For the corners, as you can see, only 3 of the corners are 1. So that means that I cannot draw it like that. But what I can do is that since I said before that the edges wrap around, I can create a circle like this that basically says that this one and this one are neighbors. You can do the same for this one and this one as well, right? Either of them is fine. The function that you come up with is going to be a slightly different, but both of them are correct. Then you can have these two in a circle, and finally for this one you can have these two in a circle. So this one is for SA. So if I want to write the function for SA, as you can see, there is none of the ones are left, right? So that makes the circling proper. So I start with the circle with the largest number of cells. So this one. In this one, the value for D3 is always 0. So we have the 3 bar. The value for D2 is both 0 and 1, so I don't include it. The value for D1 is always 1, so I have D1. And the value for D0 is going to be 1, 0. 1 and 0, so I don't have to include it. Then let's just go for this one. The value for D3 is always 0, so we have the 3 bar. The value for D2 is always 1, so we have D2. The value for D1 is both 0 and 1, so I don't include it. The value for D0 is always 1, so I have D0. What about this one? The value for D3 is always 1, so I have D3. The value for D2 is always 0, so I have D2 bar. The value for D1 is always 0, so I have D1 bar. And the value for D0 is both 0 and 1, so I don't have to include it. And finally, for the last one, we have the value for D3 to be both 0 and 1. So for this one, the value for D3 is 0. For this one, the value for D3 is 1. So D3 is not included. The value for D2 is always 0. So I have D2 bar. The value for D1 is always 0. I have D1 bar. And finally, the value for D0 is always 0. So I have D0 bar. So this is how I can come up with a function for SA. As I said again before, let's say instead of this circle, you decided to group this one here with this one, right? Your function would be slightly different, right? But both of them are correct. So this is one way that you can come up with the functions for the individual LEDs of the 7-segment display. So is it possible to use the don't care cases to even simplify this? What if for the values between 1010 and 1111 they were don't cares? So what if these are all don't cares? So let's just say you want to connect a set of data to this 7-segment display, and you always make sure that you don't input any value larger than 9, right? So if you ensure you don't input any value larger than 9, basically you can use the other cases as don't cares to simplify your function even further. So let's just consider it with don't care, and we do write the function for SA, considering if the value is greater than 9 or don't care. So for this, we first create the truth table. We write down the gray code representing the columns. And also the rows, and then we start filling up the table. So like before, we have 1 0 1 1 0 1 1 1 1 1, and then the rest are don't care, don't care, don't care, don't care, don't care, don't care, and don't care. So now we have this case. As you can see, now a lot of the cells in the truth table are don't care. So if we want to come up with the Boolean equation, we can create larger circles. So that helps us to simplify our function even more. So this is an 8-cell circle that I can draw. This is another 8-cell. For this one, I can create this 4-cell circle. And for the ones on the corner, I can create another 4-cell circle. So now if I have this and I want to write down the function for SA, for this 8-cell circle, D3 and D2 have both values of 0 and 1, so I don't include them. D1 is always 0. So I have, D1 is always 1, so I have D1 itself, and D0 has both 1 and 0 value too, so we don't have to include it. For this one, the value for D3 is always 1, so I have D3. The value for D2 is both 1 and 0, so I don't include it. The value for D1 is always is both 0 and 1, so I don't include it, and the value for D0 is both 0 and 1, so I don't include it. Then for the circle at the center, we have the value for D3 to be both 0 and 1, so I don't include it. The value for D2 is always 1, so I have D2. The value for D1 is both 0 and 1, so I don't include it. The value for D0 is all 1, so always 1, so I have D0 here. And finally, for the ones at the corners, we have D3 to be both 0 and 1. D2 is always 0, so we have D2 bar. D1 is both 0 and 1, and so it's not included, and D0 is always 0, so we have D0 bar. So as you can see, this is the final function that we can come up with. If we consider the output for the values greater than 9 to be don't cares. So let's just quickly go over the different cases that a 7-segment display can have. So the first one that we saw in the previous slide was output for inputs greater than 9 or zeros. The second case that I just explained here is that output for inputs greater than 9 or don't cares. There is another case too, in which outputs for inputs greater than 9 are shown using letters. So basically A, B, C, D, E, F. So A is representing 10, B is representing 11, C is representing 12, D is representing 13, E is representing 14, and F is representing 15. So I suggest you go and look for the LED patterns for the 7-segment display for A, B, C, D, E, F, and basically complement this table. So you put these additional rows for values that change from 1010 to 1111 with these additional rows that represent A, B, C, D, E, F instead of 10, 11, 12, 13, 14, and 15. And come up with the Boolean equations and the Karnaugh maps on your own. So this is your practice. So in this video, we learned about Karnaugh maps. We went over some of the definitions and the general rules. We saw several examples of Karnaugh maps with and without don't cares. And we also got introduced to 7-segment displays and the 3 possible cases that we can come up with the Boolean equations for 7-segment displays.